Okay, now let's consider, um, instead of having different numbers raised to different exponents, we just remember the base 10 system. So the place value system that we work in, how many? Let's go, okay. Let's go like this. That's perfect. I feel like that's enough space. Okay, so let's recall the base 10 place value system that we work in with decimals and percents. And if you want more practice with this, you can go back to the remedial video about percentages that also focuses on the base 10 place value system because you need decimals and whatnot. But what I want us to do is kind of focus on a few of these places, such as, okay, so this is the ones place, right? Which is no scale up, no scale down by 10. And how am I going to squeeze this in? You know what? I'm going to go like this, and I'm going to write this as, this is the ones place. And let's see, ones, tens, hundreds, 1000s. So this would be 10 to the first, tens, 10 by 10 makes 100. So that's 10 squared. 10 cubed is the 1000s place. Yeah. And then, okay, 10 to the fourth, to the fifth, to the sixth. All of a sudden, so now we're ones, tens, hundreds, thousands, 10,000s, 100,000s, 1 millionth place, 1 millions, place. Yeah. So ones, thousands, millions. So we're out of the 100,000 into a million. And then, okay, to the seventh, to the seventh, to the eighth, to the ninth. Let's see. So then we would be at 10 millions, 100 millions, 1 billion. So this is the billions place. I also want you to notice something awesome is that 10 cubed has 3 zeros for its place value, which is what we love about our system. 10 to the sixth has 6 places after the leading 1. So 1 million. And 10 to the ninth has 9 zeros after its leading 1, which turns it into billions. But also it works to the decimal side too, which we just saw up here, that negative exponents turn us into portions or fractions. So 10 to the -1, -2, -3. Oops, I don't want that one. I want. So if I portion down by 10, this would be 1/10, 1 100th, 1 1000th. So this would be the 1 1000th place. So it actually magically, and here's our decimal right here, right? Goes to the right and to the left with our number system. Okay, that's cool. So that's a quick recall for just of our based on place value system and what everything represents. So now let's look at some things happening. That is a little too zoomed in, my bad. But I do want it to focus again. In 1930, a national debt was 16 billion. The national debt. By 1985, the national debt grew to 1.823 trillion. Okay, and that came straight from your textbook in this section. How much more is that? Okay, so immediately I'm like, okay, we're comparing billions and trillions, but here it's 16 and here it's 1.8. Like, how do we even compare that? So gross. And there's big numbers, so I don't even know what's going on. So the first thing I'm going to do is actually write these out so that I can visually see it. You know what? Let's go purple style. 16 billion. Okay, so let's write 16 billion. And that would be 16 and then billions place. Hundreds, thousands, millions, 16 billions. Very nice. Got it. And if I'm looking at this, right, I could rewrite this as 16 times 10 to the 9th power or exponent. But if I wanted to, I could actually rewrite that. I'm going to do that in a second. I want to see what's going on with this number too, because maybe if I write it out like this, it'll help. 1.823 trillion. Oh my. So this is billion. So we still need 3 extra places. Oh, biscuits. So 1, 2, 3 to get to trillions. So got it. So now we finally have, so ones, thousands, millions, billions, trillions. Okay. So when I see 1.83823, sorry about that, trillion. Okay, well, that means 1 trillion. So that's in this place. And then we have 8, 2, 3. And then we start here. Okay, so 1, 8, 2, 3. And then we have zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and there it is in dollars. So I definitely can see that there's a significant difference. I still think here's a huge number, here's a huge number. Okay, great. Where are we on this base 10 scale? Well, when I look at this, the first thing my mind does is say 1,823 times 10 to the 9th times 10. Wait, 3, yeah. I definitely found a mistake somewhere. Anyway, oh, so automatically I see that these are a little bit easier to compare. I mean, just ignoring all of the zeros. So, right, it looks like what this did with the ability to rewrite these as exponents, it just kind of compares. If you have the same amount of zeros, we're comparing this 1800s to 16. Yeah, kind of thing. Also, here's going to be a second layer to this. So, I mean, what is that? That's like, I mean, 1600 to 1800, I mean, it's about 100 times bigger. Yeah. So when I think about comparing 16 to 1800, I'm like, it's about roughly 100 times bigger. But I also want to show you that here's another way to see that. And if we put this into scientific notation, this is close to scientific notation, but if we take it one step further, this would be written 1.6 times 10 to the 10th power. I just divided it, or I really just thought of this as being so 1.6 times another 10 is 16. So I just really was thinking about it in terms of that. And similarly here, though, if I rewrite this as 1.823, which is preferred in scientific notation, to have one leading digit ahead of the decimal is how scientific notation wants it. Then, oh, well, what did I just scale by? 10, 100, 1,000. So let's see. I am, let's see. So yeah, I put those all in the right place. Hundreds, thousands, millions, billions, trillions. Yeah. And let's see. Just double checking all of my business. I'm going to double check it all. Yeah. Oh man. What is that saying? Huh. Okay, got it. So the calculator, by the way, didn't even want to show this number like that. It showed it like this. Okay, so what did we just do? We turned this into thousands. So 1, 2, 3, 10 more, or I'm sorry, 3 more powers of 10 to make this 10 to the 12th. And now on the calculator, I want you to notice it doesn't write times 10 to the 12th. It writes E12 to represent this. Okay, so these really large numbers on the calculator are represented with this E. And then what that means is that 3, 6, 9, 12 place values larger. Okay, but now, even when we compare this 1.6 compared to 1.823, these look similar, but they're off by 2 factors of 10. So 10 by 10, if you will. Let's see. So if I'm looking at 1.6 times 10 to the 10th versus 1.823 times 10 to the 12th has a difference of 10 squared, which is 100. So this is about 100 times bigger. This 1.823 trillion. So this compared to that national debt, this is about 100 times bigger than that. But notice we didn't do a straight subtraction. You could take away 16 billion from this to get an actual number, but sometimes it is a difference of 100. So sometimes it really is nice to just compare them like this. I'm going to write it over here. This is about, whoops, you can't see that. This is about 100 times bigger. So that's one of these perks of having it written in scientific notation, is that when they're really big numbers, it kind of lets us compare how much bigger. And that tells us how many times bigger, not an exact difference, like how much is the change, but how many times bigger it is. Okay, so let's look at the Earth. Earth is about 2.57 times 10 to the 7th miles from Venus. Awkward. And it is about 4.67 times 10 to the 9th miles from Pluto. Got it. Weird notation. What's going on here? About how much further away is Pluto from Earth than Venus? Well, I feel like we can do a similar comparison. So here we go. We are doing the comparison of 2.57 times 10 to the 7 versus 4.67 times 10 to the 7. And they're both miles. So we need to make sure that we are comparing same wholes. Miles to miles, not centimeters to miles. That would not work. Or hours to miles. That's silly. So this versus this. Well, the first thing that, oopsie, this should be a 9. My bad. First thing I notice is that here it is a difference of 2 factors of 10, or 10 squared. And that means 100 times bigger. But there is a but to this problem. So 10 to the 7th times 10 squared times 100 makes 10 to the 9th. Okay, so 10 squared equals 100. Okay. So there is this 100 times bigger here, but also notice over here, excuse me, I feel like 2.57 and this 4.67, this is almost 2 times bigger than that even. So here there's a factor of 2 happening as well. So when we look at these exponents on the 10, I see a factor of 100 times bigger. And when we see these numbers over here, I see a factor of 2 times bigger. So really overall, how do we compare these distances? I would say this about how much further away is Pluto from Earth than Venus. So I would say that Pluto is about or approximately 200 times. So make sure we use this word times, further away from Earth than Venus. So this scientific notation, it can be handy. I didn't have to write it all the way out to figure this out. I could just compare these based on the scientific notation itself. So really I'm thinking, okay, this is powers of 10 right here. And this is just straight up, if we only have one decimal, we can compare this and that. Just like here, we had one decimal or one place value ahead of the decimal. So we could easily do a comparison of these and those as 2 separate parts. Kind of like looking at it as comparing all the zeros and then comparing what was left. So that's all this is really doing. It's saying compare all of the zeros, like, and that's either 100 times, 10 times, 1,000 times bigger, and then compare what's left. Yeah. Okay, so let's do another one. The number of people in the United States in 2022 was estimated to be around 323,404,000 people. Okay, took me a while to say that, right? How is that written in scientific notation? All right, well, let's work this out. So here's what I'm going to do. I'm going to take this, and actually it's already written here. So I am going to try to put the decimal right there so that there's only one decimal place there. But then the question is, how much do I have to scale that up? So 3.23404. And how many times bigger do I have to make that so that it is really 300 million? Because this is just 3. I need it to be 300 million. So that's when I go back to my place value chart and I'm like, millions. But that's just millions. I need 300 million. So I'm thinking 10 to the 8th. So I need 300 millions. And that also, by the way, this is people. I'm going to show you another way to have converted that into scientific notation, which most people are taught. So how people are traditionally taught to do this, I really do like to look at this chart and say, okay, here's a million. This is where 300 million would be, and that's 10 to the 8th power. But a lot of people were taught like, okay, here we go. If I move it this way, I've divided by 10. So I have to have a factor of 10. I move it again, I've divided by 10 again. So I have to have a second factor of 10. Divide it again. Now I have to have a third factor of 10. Divide it by 10 again to make this smaller. So I have to have a fourth factor of 10. Divide it again by 10. So fifth factor of 10. Divide it again. That was the 6th factor of 10. Divide it by 10 over here. That's the 7th factor of 10 divided by one more time to get into the desired decimal place location. And we have divided by 8 factors of 10. So we have to scale up by 8 factors of 10. And of course, if you don't trust yourself, you can always go back to this handy guy, handy robot, 3.23404 times 10 to the, oopsie, 8th. And voila. So this one actually printed it for us. So yay. So it's nice to have that too. Okay, I like it. So scientific notation. Let's write this down. How do we write down what scientific notation is? Here we go. I used some letters to explain it. So I go A point BCD because I just counted with the alphabet. Okay. Times 10 to some power n, where the first digit, A, right here in front of the decimal place, is not 0. Okay, and n is the place value directly after that first digit. N is the first place value in the place value chart, base 10 place value chart, directly after the first digit. Directly. I mean, it's how many factors of 10 you need to scale up by. So scale up by n factors of 10. Okay, that's what the n represents. I have some things that for remarks here. My first remark is that big numbers are hard to compare. We just don't live with them very often. So when we hear them, we're like in one ear, out the other. We use this tool. We use scientific notation to better understand it. Scientific notation to see how many times bigger they are from each other, to see how. Okay, so this is a way that we can compare really big numbers. And then that's really why it was developed. Let's see. Also, we use the language blank times bigger than blank, okay? Or, so if we're scaling up, it's 100 times bigger than whatever. Or we could say we're scaling down and say, or blank times smaller than whatever in our comparison. So when we're making comparisons, that's really what's up with scientific notation with large values. Maybe I should say that. Scientific notation. Okay. Scale it up, scale it down by factors of 10. With large numbers, okay, so something remarkable with large numbers, the exponents are positive. And tells us how many places, and tell us how many places to move on the place value chart. Okay, kind of like what we did here. Yeah. So with large numbers like 300 million, the exponent was positive and it told us how many places to move. So if this is saying 3, but this is large, we're going to move it 8 times to make it bigger. Yeah. So 8 scales of 10 bigger. But now let's talk about tiny numbers because these were like big numbers. Let's talk about the tiny. How much is 10 to the negative 1? Well, we actually just did all of that work to figure out what these negative exponents kind of represented. So I know now that that is 1/10, or if I use the place value chart, 0.1. What about 10 to the negative 2? Well, I know that that is now, so 10 to the negative 2 is 1 divided by 10 squared, or scaled down by 1/10 and scaled down by 1/10, or 1/100th, which is 0.01. Okay, so 0/10, 1/100th. What about 10 to the negative 3? Okay, so this is 1 decimal after. Okay, this ended up being 2 decimals. I'm guessing this is 3, but I'm going to do it the long way anyway. 10 to the negative 3, 1/10 cubed. 10 by 10 is 100. 100 by 10 is 1,000. 1,000. Tenths, hundredths, thousandth. Okay, so I'm noticing a pattern with the negative exponents as well. Cool. Rewrite 4.37 times 10 to the 4th in its place value form. Well, this has a positive, so it's a large number. So is it small or large? It's large. So just so that this is crystal clear, 4.37, this is times 10, times 10, times 10, times 10. And that means in the place value chart, right, we would go, so this was 4 times 10 times 10 times 10 times 10. This was thousands. I'm thinking it's 40,000. Okay, so, all right, so 10 tens is 100, 1,000, 10,000. So this is 4.37 times 10,000, or, well, 4 10,000s is 40,000. So 43,700. Also, if I moved over 4 decimals and then looked at the scientific notation, so 1, 2, 3, 4, and put it right here, and this would be 10 to the, this would be the 10 to the 4th place, and I put the 4 here, 4, what was it, 4.37, 43700. Look at that. Okay, so it really, it's nice like that. So this is definitely a large because we see this positive here. And in case you're like, are you sure? Well, 4.37 times 10 to the 4th. Yep. Good to go. Scale up, it says. Now this negative exponent says scale down, portion. So we have 4 holes and we're portioning it. So it's going to be tiny. I already know, because this negative exponent means we're scaling down. We're portioning. So by factors of 10. Okay. So my first instinct is to go like this, right? And take 1,000th of this. Is that 1,000th? No, 1, 2, 3, 4, 10,000th, right? So 4.37 is being scaled down by 10,000. Okay, so if we're scaling that down by 10,000, it's going to become small. Let's see. So there won't be any holes. And I had to scale it down by 10 4 times. Scale it down by 10. 1, 2, 3, 4. So that way, if I had this, so I scaled it up by 10. So that's 10 to the first, 10 to the second, 10 to the third, 10 to the fourth. Okay, so it's a tiny number, and that aligns with this idea of portioning. And just to make sure, here we go. It's this, but now I'm going to change my exponent to a -4. Oh man, it didn't even want to write it out. What if I did 4 point, how many zeros did we do? 1, 2, 3, 4, 3, 7. Ah, there's a little bit of confirmation just to be on the right track. A typical flu virus is between 1, 2, 3, 4, 5, 6, 7, 8. 8 zeros. That value and that value meters and like those are tiny, super tiny values. Rewrite these in scientific notation gladly. Okay, now I'm going to use my quick step. 1, 2, 3, 4, 5, 6, 7, 8. If I scale that up and turn this into an 8, but it's not 8 holes, it's really tiny. I scaled it up by, what did I say? 1, 2, 3, 4, 5, 6, 7, 8 factors of 10. Oh, but that's huge. Boom. Needs to be scaled down in order to be, it's not 8, it's tiny, right? It's not 8. So it needs to be scaled down by 8 factors of 10. Okay, and then what about this one? This one is, okay, so just so that we're crystal clear. Yeah. Right. And this one, okay, 1, 2, 3, 4, 5, 6. Here we go. How many, if I write it as 1.2, how many scale ups did I do to make it 1.2 instead of tiny? 1, 2, 3, 4, 5, 6, 7. Ah. Okay, but this is 8. Got it. Okay, so here it is in typical flu virus and typical, oh, that's just the flu virus. So it's between this and this. Okay, so it's somewhere between 8.0 times 10 to the -8 up to 1.2 times 10 to the -7. That's the range of how big typical flu virus is. Okay. In meters. A typical E. coli virus is about, what is that length in scientific notation? Okay, well, I can do this. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and then a 7. And if I'm going to turn that into a 7 times 10, I have to know how many factors of 10 I just accidentally scaled that up by. Well, I didn't accidentally, on purpose scaled it up by. 1, 2, 3, 4, 5, 6. Okay, so I have to make sure that in this notation, I rescaled down the 7 to get to a tiny number. Whoopsie. Bounced right off of that. Okay. So when I can even do a comparison of these two. I wonder if that's what's up on the next page. Which is bigger, the flu virus or the E. coli virus? First, find exactly how much bigger it is, then say how many times bigger it is. Okay. E. coli. let's use, so E. coli was 1, 2, 3, 4, 5, 6. Is that true? 1, 2, 3, 4, 5. Nope, absolutely not. That should be a 7. Okay. Meters in length. So here I'm going to put my label. And which we wrote down was equal to 7 times 10 to the negative 6 meters. Okay. I'm going to go for the flu with the one that looks like an 8, just so that it's, you know. So I'm going to go on the smaller end of the typical flu and go with the 0.1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. Which we said was 10 to the 1, 2, 3, 4, 5, 6, 7, 8. Okay. All right. The first, it says exactly how much bigger it is. So we're taking one and subtracting the other. I can already see that this one is bigger. So just by writing it like this is tinier because it has more portions. So E. coli, which is bigger, E. coli, by exactly how much? Well, that means we have to do a change, which is a straight subtraction. So 0.1, 2, 3, 4, 5, 7. Okay, got it. And minus 0.1, 2, 3, 4, 5, 6, 7. Oh, didn't even like us using that notation at all. So now we have to be thinking in like the calculator. Okay. So it says if we do a subtraction. Okay. Here we go. This take away that. Right on. I suppose. Here we go. I'm just going to write it. I'm going to write 7 times 10 to the negative 6, take away 8 times 10 to the negative 8, resulted in 6.92 times 10 to the negative 6. So the change, or the exact difference, how much exactly they are different. Let's go. We need to make this tiny. Okay. 1, 2, 3, 4, 5. Okay, that's the exact difference. Take away this many from there. Looks like this would be like 700. So it's 100. I see it's 100 times bigger because this is negative 6. 2 factors of 10 difference. So then it says, say how many times bigger it is. So I notice that, I mean, 7 and 8 are comparable. They're not exactly the same, but this is a pretty big deal. There's a difference in a factor of 100. So what I would write is the bigger one, E. coli, is about 100 times bigger than flu virus in meters. Lovely. Cool. I feel like that's easier to say than that. So just another reason why the scientific notation is quite helpful. Compute the percent change from the smaller virus to the bigger virus using this formula. Oof. Well, luckily we just did this bigger minus the smaller and got that. And then we're going to compare it to this smaller. So here we go. Percent change, or the percent difference. Bigger minus smaller is right here. 6.92 times 10 to the negative 6. And we're comparing that to the smaller virus, which was the flu. 8, oopsie, I don't need any decimals, but times 10 to the negative 8. And then we multiply by 100 to make it into a percentage. Huh. Let's see here now then yet. Well, actually, this could go up and this could go down based on our rules of exponents that we just figured out in videos 1 and 2. So we got a 6.92, and this b times 10 to the 8th, and this, so 8.00, and because if you remember, right, having a negative in the numerator means that it's being scaled down, so that would go in the denominator. Oopsie, why did I do that? And then if you are doing the opposite of scaling down, you're scaling up, so there's that. And now this can actually simplify. This is a factor of 100 different, actually. So I'm going to go ahead and punch this whole thing into the calculator. Here we go. 6.92 times 10 to the 8th power. Okay. Oopsie, no. Delete that. No. No. Delete, delete, delete. 8th power. There we go. And then divided by the quantity, 8.00 times 10 to the 6th power. And by the way, you could have just done that all in this step too. And then times 100. 8,650. Interesting. 8,650%, because it's a percent change. So, oh, this ended up being a really nice division of that amount. Cool. Nonetheless, so this is, whoa. So that means E. coli is 8,650% increase from the size of the flu virus. That's a lot bigger. I like, it's just a different way of saying it. This one compares it to the size of the flu, compares E. coli to the size of the flu, in a different way as a percentage, instead of thinking of it in terms of scientific notation as 100 times bigger. Cool. All right. And then I thought this was kind of clever of your textbook, so I wanted to include a couple of these. I did it a little different than they have. This example of translating scientific notation into words. But I did want to include this because I thought it was pretty good. Okay. 1.60 E. So your calculator says E10. So I want to immediately write this as 1.60 times 10 to the 10th is what that means. And if we go back, right, okay, to the 10th. So we have hundreds, thousands, millions, billions. Okay, so if we have, so we have more than billions because we're in the 10th, 16, 10 times more because it was one place value more. Boop. So 10 times bigger, 16 billion dollars. Okay. Oof. And my mind also did this. So while I was thinking about it and just said it out loud, and 10 to the 9th is a billion. Okay. Ooh, then what if it's negative? Kind of like these viruses, yeah? So that means it's going tiny. So if we go the other way, but in moving so, we're going to end up, let's see, as, okay, so let me write this. So 1.60 times 10 to the negative 10 is what we're looking at. And I kind of want to do a similar thing here where I rewrite this as 16 times 10 to the negative 9th. And this would be 16 billionth of a meter. A 16 billionth of a meter. That's kind of cool. So tiny, really big, really small. And now 3.23 E 12 miles versus 3.23 E negative 12 miles. Now I wanted to show this for a very, very specific reason, because I want you to, right. So, okay. So 3.223 times 10 to the 12th. To the 12th power, what is that? Trillions? Ones, thousands, millions, billions, trillions. So that is immediately in trillions because it's to the 12th power. So I'm going to say 3.223 trillion miles. Got it. And then 3.223 e to the negative 12. So I was just thinking to myself, yeah. So it's already to the negative 12th power. So straight to trillionth. So let's rewrite this. 3.223 times 10 to the negative 12. Rewritten, and 3.223 trillionth of a mile. Okay, oopsie, that should be a 12. So I kind of like that about our base 10 place value system and the scientific notation. A couple of remarks: be careful with some exponents. So these are just a couple of bewares. So careful that when you see something like this, 5 times 2 cubed, that you remember the order of operations, and that this is really 5 times 8. You have to do the exponents before the outside multiplication, and that it is not 10 cubed, which is 1,000, or so here I'll write 40. Okay, and that's correct. So that's supposed to be a smiling face. And but it is not. So it is not 10 cubed, which is 1,000. And it is not, another mistake I see is people accidentally doing 2 times 3. So this is not 30 either. This is 2 times 2 times 2. So remember that when we have exponents, we need to be more careful. We need to really think about what we're doing there. And then I have another remember, and that was what this whole thing was kind of founded on, this idea that when we're dealing with exponents in scientific notation, repeated addition, looks like this and is represented as multiplication, but repeated multiplication is represented with exponents instead. So just remember the difference there. Okay, so in a nutshell, you represented values using exponents, performed operations on expressions with exponents, used properties, and you converted decimals and scientific notation and interpreted those values, all in this section of exponents and scientific notation.